Good morning, sir. Good morning, sir.
Morning, all of you. So, last class we have been discussing about uh, coordination compounds, right? So, today we will be continuing with our discussion. So, last class, if you remember, we were discussing about color properties. Yes or no? So, what is responsible for the color? Can anyone say?
DD transition.
DD
DD
transition.
Very good. The DD transitions, that means the transition of electron from one d orbital set to the other d orbital, that will be making the compound showing its color. So presence of ligands are required for the DD transitions. Why? Without ligands, you can write down this statement. Without ligands, there is no splitting of d orbitals. Without ligands, splitting of d orbitals will not occur. Splitting of d orbitals will not occur. So if splitting of d orbitals will not occur, obviously splitting of d orbitals will not occur. Obviously, no DD transition is possible. So on this context, we have said the presence of ligand is required for the DD transition. An example we have discussed: titanium trichloride TiCl3 is going to be colorless, but when you add that to water, it will form a complex which is colored in nature, because in this complex the DD transitions are happening, and when you heat this complex, all the H2O molecules will be again lost, and you again get TiCl3 which is going to be colorless. So without the ligand, there is no DD transition. Example of copper sulfate also we have seen. Copper sulfate is colorless. In the hydrated form, it will form a complex where the DD transitions are possible. So it should be color. It is light blue in color. Again, if you heat it, again it becomes anhydrous CuSO4, which is again colorless in nature. So then comes the principal charge transfer spectrum or charge transfer phenomena. Some compounds of D block metals shows color due to charge transfer from cation to anion. From ligand, write down, from ligand to metal. Some compounds of D block metals shows color due to charge transfer from ligand to metal. So write down these example, students. These are important. Like you should know the colors at least. KMnO4, potassium permanganate, dark violet in color. K2Cr2O7, orange color. Na2CrO4, yellowish color. CrO2Cl2, that is reddish orange in color. If you look at this, we have already discussed, like in D block, MnO4 minus K plus. In MnO4 minus, what is the oxygen state of manganese? 1 manganese, 1 into X.
+7.
Yeah, 4
Yes,
oxygens,
sir.
4 into -2, that is equal to -1. So X should be is equal to +7. So in MnO4 minus, manganese is in +7 state. It is double bonded with oxygens, and we have O minus. So it is Mn plus 7. What is the electronic configuration of manganese? Argon 4s2
Yes,
3d5.
25.
In the +7 state, it will simply have argon. So if it simply has argon electronic configuration, is there a d electron? No d electron. So it should not be colored. Yes or no? But it is showing color. It is dark violet in color. Why? Why? Because of
ligand
ligand to
to
metal charge
metal
transfer.
charge transfer
Yes. How the charge transfer occurs?
by donation of electrons from
By
oxygen.
donation. Yeah, very good. By donation, charge transfer means the charge is transferred with the help of electrons, by the virtue of electrons. Okay. From the oxygen, the electrons have been transferred. So, from oxygen to manganese, charge transfer occurred. Charge transfer occurred, and because of that, color is shown. Compound colored complexes obtained. Now again you have a question. Sir, everywhere you will be having the such scenario. Charge transfer phenomena is going to happen for all the complexes or only few? Only few compounds, whatever we have listed here. Yes or no? And we are going to add a few more examples in the upcoming classes. It is not like the charge transfer phenomena. It depends upon symmetries as well. Yes or no? Because here whatever the molecules are considering, in every molecule you have the molecular orbital. You are talking about molecular orbital. So this charge transfer phenomena stands as the foundation to the next theory known as molecular orbital theory. Although that molecular orbital theory of complexes is not in our syllabus, but it is actually standing as a foundation to the next theory also. So the molecular orbitals, what molecular orbital theory says is same with the crystal field theory where you have electrostatic force of attraction. According to molecular orbital theory, the molecular orbitals are formed. They arrange in space in the order of increasing energy. Then only you will be having the filling of electrons. So these molecular orbitals and filling of electrons in those molecular orbitals again has to be decided by symmetry. Or at least you have studied MOT from your chemical bonding, right, students? Yes or no?
Yes.
In the chemical bonding, you will be dealing about 1s, 2s, 2p. We are not going beyond 2p. We are making atomic orbitals involved in the mixing part and generating molecular orbitals only 1s, 2s, 2px, 2py, 2pz. Because whatever the molecular orbitals form, based on the symmetry of the molecular orbitals, the arrangement of these orbitals changes, which is complex and not in your syllabus. So we have to stick with these examples as of now and their colors. KMNO4, K2Cr2O7, Na2CrO4, CrO2Cl2, they are all colored and they have the colors like violet, orange, yellow, reddish, orange. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, very good. So this will be explaining the color property of your complex compounds. Then comes the isomerism. Isomerism, you again have two parts, structural isomerism and stereoisomerism. Structure means what? A difference in the structure will be there. Difference in, by the name itself we can say, difference in structure. Stereo means
Difference
what
in
else?
arrangement.
Difference in spatial arrangement. Difference in spatial arrangement. So let us look at these categories. Can you list out the same isomerism in your organic compounds? What are the structural isomers?
Tautomers, metamers.
Yes. Tautomers, metamers.
Functional group.
Functional group.
Linkage.
Linkage. Linkage is there in your organic compounds or here?
No, I actually spelled out metamer.
Okay. So write down here, there you will be having chain isomerism, position isomerism, functional group isomerism, metamerism, ring chain isomerism. Yes or no? All these are there in the organic compounds or organic chemistry. Whereas here you will have the different names: structural isomerism, ionization isomerism, linkage isomerism, hydrate isomerism, coordination isomerism. List down this, very, very important. Stereoisomerism is again classified in two types: geometrical isomerism and optical isomerism. Stereoisomerism, how it is decided in organic compounds, we should know the analogy.
Generation of
Stereoisomerism.
carbon samples.
No, I am not talking about all that optical activity. So how the classification of stereoisomerism has been done? Two types: configurational and
Configuration.
conformational. Yes. Configurational, again of two types: geometrical, optical. So geometrical, here you will have cis trans isomerism. Here also you have geometrical isomerism. Here also you have optical activity or optical isomerism. How we can say geometrical isomerism in your organic compounds?
By this analyzing stereo centers.
Stereo centers. What is the reason for the cis-trans isomerism? Is the restricted rotation around carbon-carbon
Carbon.
double bond.
Double bond.
So if you look at a single bond, carbon, single bond, carbon, because the analysis is important, students, we are just comparing how we can understand geometrical isomerism, optical isomerism, and structural isomerism of coordination compounds with the organic compounds. So whenever you compare carbon-carbon single bond, like you visualize this pen, this is one carbon, this is other carbon. On this carbon, we have three groups. Let us say CH3, CH3. What are the three groups connected to this carbon? Three hydrogens. Yes or no? 1, 2, 3. Three hydrogens are connected to this particular carbon. Whatever the other carbon? The other carbon also has three hydrogens. This carbon and the other carbon, they are connected by a single bond. Carbon-carbon single bond. No molecule is static. Yes or no? All the molecules are moving with different velocities. Now what I am going to do is, I am going to rotate this particular carbon with respect to this carbon. What I am doing, students? Let us say this is carbon 1, like C13, C14. I can take the isotopes, right? Carbon 12, carbon 13, carbon 14, C13, C14. Let us say C13 will have a different angular velocity. It wants to rotate. It is not static. It is not fixed in space. Let us say C13 is this one. It is rotating with different angular velocity. C14 is rotating with different angular velocity. Let us say omega 1 is the angular velocity of C13. Omega 2 is for C14. Both are rotating in the same direction, let us assume. Now with respect to C14, let us say with respect to C14 we'll look at now. Or with respect to C13 we can look at now. If you look from the outside, if you are out of the frame of C13 and C14, like me visualizing this molecule C13 and C14, for me C13 is rotating, C14 is also rotating. Now you go and stand on C13. If you are standing on C13, with respect to you C14 rotates. That means you are static. For you, you are going to be static. You have just changed the frame of reference. Earlier the frame of reference is outside, now you went into the frame. When you look from the C13, the C14 will be alone rotating. When you look from C14, C13 will be alone rotating. That is where the concept of relative velocity comes into picture. So if you try to look at the relative velocity, like in that case, you will have one carbon atom fixed. With respect to this carbon may be rotating. Yes or no? Are you understanding these points or not?
Yes, sir.
Rotation of two carbons I am visualizing now by standing on one of the carbon atom. On whatever the carbon I was present, I am static. That means that carbon is not moving with respect to my frame of reference. If I am in train is not moving for me. Only thing is the trees are going back. If I am outside of train is moving for me. That is the logic you need to understand. If I am standing on C13, then for me C13 is not moving. It is not having any velocity. I am static. Because I and C13 both have same angular velocity, same rotational velocity, everything is same. But for me, what is happening? C14 is moving. C14 is having some rotation. So with respect to one carbon, you try to move the other carbon. That's what I'm saying. I'm keeping this particular carbon fixed. I'm moving the other. Because of this motion, this bond disturbed. The carbon-carbon bond. This is the bond, right? The pen is the bond, as I have told you. This is carbon, this is carbon. This is a carbon-carbon bond. So this carbon is static. This carbon is under motion. Because of this motion, is this bond moving or disturbed?
No, sir.
No, right? So carbon-carbon single bond can be easily movable. That means rotation around carbon single bond is free. Single bond is free. You try to now rotate the same scenario with respect to carbon-carbon double bond. How the double bond is formed, students?
Overlapping of pi orbitals.
Yeah. What is the hybridization here now?
sp2.
sp2.
sp2 hybridization. So write the electronic configuration of carbon. Carbon is 1s2, 2s1, 2px1, 2py1, 2pz1. In the excited state, the 2s, 2px, 2py, they involve in the hybridization. They form 2s, 2px, 2py, 3 atomic orbitals involved in the hybridization to form how many hybrid orbitals? 3 sp2 hybrid orbitals. These 3 sp2 hybrid orbitals will arrange in the space in such a way such that repulsions are minimum. So how the repulsions are going to minimum? So you'll have one sp2 hybrid orbital like this. The other will be like this. The other will be like this. I am drawing this sp2 hybrid orbital more like p orbital because it has more p character. Similarly, I have another carbon where it has one more sp2 hybrid orbital, sp2 hybrid orbital, sp2 hybrid orbital. This is your carbon. This is your carbon. In every carbon, you have 2pz which is empty, like 2pz which is not involving a hybridization. So the 2pz is as it is. Here also 2pz is as it is. So what happened to this? 2pz, 2pz. The 2pz, 2pz overlap sidewise to form a pi bond. What is a carbon-carbon double bond? Carbon-carbon double bond has one sigma bond, the other is pi bond. How the sigma bond is formed?
Head-on-head overlapping.
Yeah, head-on and overlapping of what?
S and p orbitals between
S.
carbon and hydrogen.
In the carbon-carbon double bond, one is sigma, the other is pi. How pi bond is formed? The 2pz atomic orbital of one carbon overlaps with the 2pz atomic orbital of another carbon. How the sigma is formed?
Head-on-head overlapping of carbon S hybrid orbitals.
sp2 hybrid orbital of one carbon overlaps with the sp2 hybrid orbital of another carbon. What about CH bond?
Sigma bond. P and S between P and S.
sp2 hybrid orbital of carbon with the s orbital of hydrogen. Similarly, all the 4 CH bonds are formed by sp2 hybrid orbital of carbon with the s orbital of hydrogen. Now you look at the overlapping. So here we have a carbon atom like C13 carbon. This is C13 carbon now. This is your C14 carbon now. Now go and stand on C13 carbon. So with respect to C13, you are at rest. So C14, you try to move. Earlier you have only a single bond. Now we have double bond. In the double bond, one is sigma, the other is pi. How is sigma bond formed? sp2 overlapping, which is along the end-on-end overlapping. So this is your sigma bond now. How is pi bond formed? Pi bond was somewhat like this. Yes or no? Sideways overlapping. My fingers. So whenever you try to keep this carbon fixed and try to rotate the other carbon, what is happening? The pi bond is disturbed or not? Yes or no? If you want to rotate the carbon-carbon double bond, in the process of rotation, you are going to disturb the overlapping of 2pz, 2pz. Are you understanding this point?
Yes, sir.
Yes, sir.
In the process of overlapping, in the process of rotation, the overlapping of 2pz, 2pz is disturbed. So free rotation around carbon-carbon double bond will not happen. So since the free rotation is not happening, whatever the groups present on this side, like if I have methyl here, that will be methyl only. If I have methyl here, that will be methyl only on this side. So if since the rotation is not possible, this methyl stays here only, this methyl stays here only. So they are exactly opposite to each other. So what they are constituting? They are constituting trans isomers.
Trans isomers.
That means the cis and trans, cis means same side, trans means opposite side, that is obtained because of restricted rotation around carbon-carbon double bond. If the rotation is free, there is no point of cis and trans because the groups are changing their positions continuously. Since the rotation is not free, the groups present on one side, they are staying on one side only, and whatever the groups present on the other side, they are staying on that side only. So cis and trans arise here due to restricted rotation. But what about cis and trans here in the stereoisomers or coordination compounds? Like in the stereoisomerism of coordination compounds, do we have restricted rotation of carbon-carbon double bond? We do not have such scenarios. Here we are going to define cis and trans on different motive. Whereas cis and trans in organic chemistry is based on the restricted rotation about carbon-carbon double bond. Cis and trans here is defined on a different basis. What is that basis we are going to look at? And optical isomerism, what is optical activity?
dextrorotatory and levorotatory. In ancient
what is that?
Greek,
So the
Uh,
compound,
rota-
if it has, if a compound has a
Rotation
tendency,
under plane polarized light.
very good. If the compound can rotate the plane polarized light, it is said to be optically active. How to
optical
figure it out? Yeah, how to, like we say the statement, but how to figure it out whether the compound is optically active or not?
by passing plane polarized light, the angle at which it
Yeah, Faizan
rotates.
Khan, we are not going to use the apparatus to you. Okay. In the exam, I'll give a question, I'll give simple compound to you. You have to figure it out whether it is optically active or not. If
If
we,
it forms
Chiral
Chiral
non-superimposed,
carbon.
center. Chiral carbon
yeah,
for different group will be
yes, Suman?
Chiral carbon.
different group will be there in chiral carbon.
Yeah. So optical activity means simple statement is optical activity is the ability to rotate the plane polarized light either by clockwise or anti-clockwise direction. Clockwise dextrorotatory, anti-clockwise levorotatory. But how to figure out a compound is optically active or not? There are some conditions. If only one chiral carbon is there, is it optically active or not directly?
active.
For only one chiral carbon means a carbon which is connected to 4 different groups. For only one chiral carbon, directly optically active. Directly optically active. If more than one chiral carbon is there, what you have to do?
Symmetrical plane.
RS rotation.
Symmetry elements. Yeah, symmetry elements. More than one chiral carbons. More than one chiral carbon. Look at elements of symmetry. What are the elements of symmetry? Plane of symmetry, center of symmetry, axis of symmetry, and all. Okay. So if the compound, organic compound given to you and figure out optical activity using experimental analysis, you can pass the plane polarized light, check whether it is rotating clockwise or anti-clockwise. If the rotation is there, you can confirm it is optically active in nature. But instead, if the compound molecular formula is given to you or molecular structure is given to you, and if you have to decide whether it is optically active or not, the initial idea is chirality. So whenever a compound has only one chiral carbon, whenever it is having only one chiral carbon, it will be optically active. It will rotate the plane polarized light. If it has more than one chiral carbon, then you have to go in the elements of symmetry. If the compound has a plane of symmetry or center of symmetry or axis of symmetry, generally plane of symmetry and center of symmetry were looked most into. In that cases, if the compound has plane of symmetry or center of symmetry or axis of symmetry, what we can say? One part of the molecule compensates the optical rotation of other part. As a whole, the total molecule will be not rotating the plane polarized lights. Understood this point carefully? Like if you have two compounds or two chiral centers. So this is chiral center A, this is chiral center B, and everything is same. This connected to X, Y, Z. This is connected to X, Y, Z. I'll pass a plane like this. If I pass a plane like this, this plane is dividing the total molecule into exactly two parts or not. This plane, whatever the mirror plane I'm passing here, that is exactly separating the total molecule into two equal planes, which are said to be mirror images. Yes or no? And this is nothing but your plane of symmetry. Yes, this is nothing but your plane of symmetry. So if the one part of the molecule is rotating the plane polarized light by an angle theta in the clockwise direction, since it is a mirror plane, the other part will rotate by the same angle theta, but in the anti-clockwise direction. So what happens to net rotation?
0.
Net rotation will be 0. So whenever you have a plane of symmetry or center of symmetry or axis of symmetry, the molecules are going to be optically inactive. If we do not have any symmetry elements, then the molecules are said to be optically active. So same logics you are going to apply here in optical isomerism. If you want to check whether the molecule is optically active or not, you have to look at plane of symmetries. Understood, students? This is the comparison of your stereoisomerism with your organic compounds. Just note it down. Then we'll be starting with one by one: structural isomerism, ionization isomerism, linkage, hydrate, coordination, and then we'll proceed to geometrical and optical. Done or not?
Yes, sir.
Yes. Structural isomerism, look at same formula, same chemical formula will be there, but structure will be different. By the name itself, we can understand that. Types of structural isomerism, ionization isomerism. Very easy statement. Ionization isomerism means compounds having same chemical formula is same, but give the test of different types of ions in aqueous solution. That is known as ionization isomers. Whatever the molecules you have, whatever the complexes you have, CONH3 taken 5 SO4 bromine, CONH3 taken 5 BrSO4. When you treat this with AgNO3 and BaCl2, in the first complex you are getting AgBr. In the second complex you are getting BaSO4. That means if you test the first complex, for sulfate test, negative or positive will be given?
Negative.
Negative. For bromide,
Positive.
Positive.
positive. So the first complex has the same chemical formula, like CONH3 taken 5 SO4Br, with same as that of second complex. But if you look at the dissociation, here bromine is acting as a counter ion, so it can be given as bromide ion, whereas sulfate is present in the coordination entity, or it is acting as a ligand. You are not going to get sulfate ion, so SO4 2 minus, that will be showing negative test, whereas bromide will be positive. Second compound you will get positive for sulfate, positive for SO4 2 minus, and negative for Br minus. Why? Yes, very good. Why? The dissociation can give you answers. The first compound dissociates to give complex ion and bromide ion. Second complex dissociates to give complex ion and sulfate ion. And in this first complex, SO4 is acting as a monodentate ligand or a bidentate ligand? Monodentate ligand, very good. Because already 5 ligands are there, ammonia. The sixth ligand, SO4, should be a SO4. That means SO4 should be acting as only one more ligand. So only one more coordinate bond should be formed, monodentate ligand. And if you look at the scenario, compounds having same chemical formula but give the test of different types of ions in aqueous solution, they are known as ionization isomers. Is that clear, students?
Yes, sir.
Yes, very simple, right? So you can have CONH3 taken 5 SO4 Br plus AgNO3. Whenever silver nitrate is added, you are going to get AgBr silver bromide. Similarly, whenever you have a different complex and you add barium chloride, you are getting barium sulfate. Yes or no? Barium sulfate is going to be obtained, which is a white PBT. Hydrate or solvate isomers. What is this? Special type of isomerism in which number of water molecules or polar molecules differ in coordination sphere or outside region. So look at these examples. Chemical formula of complex COCl3 or 6H2O. I can have this complex in different manners where all the 6H2O are acting as ligands. Out of 6H2O, 5 will be acting as ligands, 1 chlorine will be acting as ligand, 4H2O will be acting as ligand, 2 chlorine will be acting as ligand. Yes or no? 3H2O will be acting as ligand and 3 chlorine will also be acting as ligand. So what are the possibilities? Look at the possibilities. But can I write this molecule COCl3, H2O taken thrice? Can I write this molecule? Can I write the molecule like this and include that in the hydrate or solvate isomerism? Like all the three H2O All the 3 chlorines I am including as ligands and 3H2 as ligands, and the remaining 3H2 outside, the hydrated. So this is not possible. This is not included in the hydrate isomerism, because the condition is special type of isomerism in which number of water molecules or polar molecules differ in coordination sphere or outside region. So in the coordination sphere, whatever the H2O you have, and in the outside region, whatever the H2O you have, they cannot be same. So since H2O is 3 again inside and outside, so it cannot be a hydrate isomerism. Understood this point or not?
Yes, sir.
Yes, sir.
Okay. Yes, because H2O inside the coordination sphere and outside the coordination sphere are equal in number. The number of H2O inside the coordination sphere and outside the coordination sphere, they are equal in number. That is why this is not included in the hydrate or solvate isomerism. All right, students. COCl3.6H2O. This is the formula. So all the 6H2O, like first case, this is what type of formula is this? It is nothing but CO, H2O taken 6. All the 6H2 are acting as ligands, and all the 3 chlorines are outside. So hexa aqua cobalt 3 chloride, yes or no? And we have the other compound where 1 H2O has been replaced with 1 chlorine. Next molecule, the other H2O and the other chlorine, they have been replaced. If you try to replace other, yes or no? You have 3 chlorines inside and 3 H2O inside and 3 H2O outside. So this you cannot include. This you cannot include in the coordination hydrate isomerism. So hexa aqua cobalt 3 chloride, penta aqua chloro cobalt 3 chloride monohydrate, tetra aqua dichloro cobalt 3 chloride dihydrate. So these are the 3 examples of hydrate isomers. Write down this. Hydrate isomers of COCl3.6H2O. So how many hydrate isomers are possible? 3 hydrate isomers are possible. What are they? These are the 3. So sometimes the questions can also be twisted, like they can give the names: hexa aqua cobalt 3 chloride, penta aqua chlorido cobalt 3 chloride monohydrate, tetra aqua dichlorido cobalt 3 chloride dihydrate. All these 3 are hydrate isomers or not? Like that. Instead of giving the molecules to you, instead of giving the formula to you, they can give the IUPAC names. From the IUPAC names, we should be in a position to write the formulae and then figure out whether the number of H2O molecules are differing inside and outside the coordination sphere or not. Clear? Only condition is same number of solvent molecules should not be there. Yes. Linkage isomerism. Can we say this is due to what? The linkage isomerism. Yes, Aishi.
Ambidentate ligands.
Ambidentate.
Very good. This isomerism arises due to the presence of ambidentate ligands. So whenever the ligand has 2 centers, 2 electron donor centers, but they cannot be donated at the same time, then you can have the ambidentate ligands. Examples of ambidentate ligands we are already given. Cyanide CN minus NC minus, OCN minus NCO minus, SCN minus, NCS minus, ONO minus, NO2 minus. So these are your ambidentate ligands. Write down all of you. Linkage isomerism. This arises due to the presence of ambidentate ligands. Like in a complex, if I have like K4FeCN6. Here, what is the species which is undergoing the linkage? Carbon or nitrogen?
Carbon.
Carbon. You have this. You have the same examples, even linked with the cyanide and NC minus. If you look at the reaction, students, you have the importance of cyanide and isocyanate even in the reactions of organic chemistry, alkyl halides. In the reactions of alkyl halides with the KCN and AgCN, let us take a reaction of an alkyl halide, RX, treating with your KCN, and take the reaction of alkyl halide, RX, with AgCN. Can you explain what happens in the first case? Can anyone explain what happens in the first case?
First case cyanide and second case isocyanate.
Why?
Because the Ag and C bond is second case is covalent in nature.
Very good. So what Suman says is, in the AgCN reaction, like these are also acting as a ligands, these are also acting as nucleophiles. We are calling them as ligands in your organic chemistry, in your coordination compounds. We are calling as nucleophiles in your organic chemistry. They are ambidentate ligands in your coordination compounds. They are ambidentate nucleophiles. Yes or no? Ambidentate nucleophiles in your organic chemistry. So you have the attack happening from the nitrogen side as well as the attack happening from the carbon side. Now you take KCN. KCN is ionic in nature. Since KCN is ionic in nature, it produces what type of ions? K plus ion and Cn minus ion. AgCN, is it ionic in nature? No, it is covalent in nature. So we have Ag connected with carbon and carbon connected with nitrogen with a triple bond. So if you look at AgCN, here carbon is already bonded with the silver. So the carbon silver bond is not broken. So the attack of the nucleophile is not possible from the carbon side. It is only possible from the nitrogen side. In the alkyl halide, like RX bond is there. Halogen is more electronegative. So partial negative on halogen, partial positive on carbon. Partial negative halogen, partial positive on carbon. So here if you look at the AgCN attack happens from only nitrogen side. So it will lead to the formation of R and C only. Isocyanates are only obtained. So this is what Suman says, that is completely fine. I agree with that. But in KC and Suman, we have K plus and Cn minus. In Cn minus, the attack can be from carbon side as well as from nitrogen side. Why it is not from nitrogen side now? Yes or no? Here carbon side can also attack, nitrogen side can also attack. Earlier we said that carbon is already linked with silver, so there is no possibility of carbon to attack the alkyl halide again. So that's why we have eliminated the carbon attack and only nitrogen attack has been taken. So isocyanates are only formed. Isocyanates are only formed. Now if you look at the KCN scenario, we have K plus and Cn minus. So the attack is happening only from the carbon side, forming to the formation of RCN, because if the carbon side attacks, we lead to the formation of carbon-carbon bond, which is going to be stronger bond. Why? Due to stronger overlapping. Okay. Write down those points. In KCN, Cn minus attacks from carbon sides, attacks from carbon site, because carbon-carbon bond formed will have more overlapping. The whatever the carbon-carbon bond is formed, that is going to be stronger bond due to stronger overlapping. Any other reason you can cite?
So
Overlapping is great.
electronegativity of carbon.
Very good. Less electronegativity of carbon, and carbon is less electronegative. Because of less electronegativity, what happens?
More donating tendency.
Very good. Carbon is less electronegative and its electron donation tendency is less, is more, and its electron donating tendency is more. Okay. So that is the scenario, students. Whenever you have KCN and AgCN attack, we are going to have such type of scenarios. So whatever the species which is less electronegative in nature, less electronegative means it can't withstand or withhold the electron density on itself. So it will be useful in the attack easily. So the carbon being less electronegative when compared to nitrogen, it wants to be more nucleophilic in nature, and that is where the attack is happening from the carbon side. And also the carbon-carbon bond which is formed, that will have stronger overlapping. So great overlapping leads to stronger bond. Understood? This is an example. This was just an example which can give you an idea of how KCN and AgCN they are going to be reacting with alkyl halide RX. But here that was different. This is organic chemistry reaction where you are thinking of attack of cyanide ion as an ambident nucleophile. But now we need to think it of ambident ligand. Same thing. Here the attack can happen from carbon side and nitrogen side in organic chemistry. And now here in the linkage isomerism, the electron donation can be from nitrogen side or from the carbon side to the central metal ion. So these are nothing but ambident ligands, ambidentate ligands. So let us, can I proceed further, students?
Yes, sir.
Yes. Yes, very good. So metal metal cyanide bond is there. So cyanide is donating the electrons to the metal and the donation happening from the carbon side. Again, the isocyanide is forming. So from the nitrogen side also electrons can be donated. So where nitrogen is donating the electrons, so you will be forming the isocyanates. So metal cyanide bond, metal isocyanate bond, these are nothing but your ambidentate ligands. Yes. Whenever it is the donation from carbon side is said to be cyanido. Whenever the donation is from nitrogen side, it is said to be isocyanido. Got it, Keshav?
Yes, sir.
Yes. Example you take PTNH3 taken twice, NO2. PTNH3 taken twice, NO2 taken twice. PTNH3 taken twice, ONO taken twice. NH3 is a monodentate ligand. NO2 is also a monodentate ligand. But NH3 is a monodentate ligand, and it will be donating only from nitrogen center. So it is not ambidentate. But NO2 is monodentate and ambidentate. So in NO2, the donation can be from oxygen side as well as from nitrogen side. So look at the PT-NH3 taken twice, NO2 taken twice. And look at the respective linkage isomers. NH3 is always linked from the nitrogen side. So PT-NH3 taken twice only. In NO2, both the can be linked by oxygen side. So ONO taken twice. NO2 taken twice is one case where both the linkage is happening from the nitrogen side. ONO taken twice is other case. ONO taken twice where the linkage is happening from the oxygen side in both the compounds. One NO2 can be from the nitrogen side, the other can be from the oxygen side. Yes or no? So like you are having complex like this. PT-NH3, NH3, NO2, NO2. PT-NH3, NH3, ONO, ONO. Whenever we say ONO, it is the oxygen linkage. We can also have a complex PT-NH3, NH3, ONO, NO2. Understood or not? So in both the cases, we can have NO2, nitrogen can be linked. In both the cases, we have ONO, oxygen can be linked. In one case, you can have nitrogen linkage, and the other case, you can have oxygen linkage. So these are the three different examples of ambidentate ligand, like where NO2 is used. These are the three different linkage isomers for this compound. Can you write down the linkage isomers for this compound CONH3 taken by CN? How many linkage isomers are there?
Two.
Two linkage isomers. Yes,
Two,
or no?
sir.
Because only one.
Yes, sir.
Only one. Yes, only one ambidentate ligand is there. So in case of only one ambidentate ligand, what is going to happen now? We can have CN or we can have NC. That is the only possibility. We can't have, if you have more than two, like CN2 is there means, if you have CN2, in that case we can have both the cyanates, both the isocyanates, one cyanide, one isocyanate, like that we can have examples. But now here only one
Sir, we can have
ambidentate. Yes, Suman.
sir, we can have ionization isomer also, no?
We can have ionization. Yes or no? That depends upon the type of ligands, whatever we have taken. Yes or no?
We can exchange CN and SO4 minus 2 minus.
Yes, obviously no. So here we are having CN and here we are having NC. Yes or no? In the two complexes, one complex ion is having the linkage with CN, the other complex ion is having the linkage with isocyanate. So the SO4 2 minus is same, but the complex ions are different. Yes or no? If you write the dissociation, what you are getting? CONH3 taken 5, CN whole plus 2 plus SO4 2 minus. If this is dissociates, you get CONH3 taken 5, NC whole plus 2 plus SO4 2 minus. But you have to categorize them, these two compounds, whenever they have given what are they, and different options are given, then you have to give priority to linkage. Okay. Whenever linkage and ionization both are there, then preferentially choose ionization. Got it or not?
Okay, sir.
Yes.
Yes. Coordination isomerism. Then the next type of structural isomerism is coordination isomerism. Then this isomerism arises due to exchange of ligands between complex cation and complex anion. So we have a complex cation and we have a complex anion. Ligands can be exchanged. You can write down the example and I'll give a shortcut to you to calculate the number of coordination isomers. So what happens in this case, students? CONH taken 4. Can I have a complex like this? Ammonia can I exchange? Can I write like this or not? CONH taken 4, COCl4. We can have an exchange like this. We can have one ammonia exchanged with one chlorine. Ligands have been exchanged. Now we can also have the exchange like this. Can you say this is a different compound? All of you note it down. Can you say this is a different compound?
No, sir.
So we can have the shortcut formula to find out how many number of coordination isomers are possible. How many number of coordination isomers are possible, students? Write down this formula. Number of coordination isomers is equal to coordination number for a different central metal atom. For different central metal atom. So if central metal atom is different, then whatever the coordination number you have, that will be equal to your number of coordination isomers. Coordination number by 2 for identical central metal atom. Yes or no? Here the only trick is whenever we have same number of ligands. So this was not actually included in the coordination part. Yes or no? So here we have same central metal atom. CONH taken 4, COCl4. So what is this? Same central metal atom. So number of coordination isomers is equals to coordination number by 2. What is the coordination number here? CONH taken 4, COCl4. Coordination number how much? Coordination number. If you look at the coordination number, it is 4. Yes or no? NH taken 4, Cl4. So coordination number by 2 when we have identical central metal atoms. So what is the number of coordination isomers? 4 by 2. So here we have 2 isomers. All of you note it down, students. Coordination isomerism. This isomerism arises due to the exchange of ligands. This isomerism arises due to the exchange of ligands between complex cation and complex anion. Number of coordination isomers is equals to coordination number for different central metal atom, that is equals to coordination number 2 for identical central metal atom, and this is applicable only in the case of monodentate ligands. This is applicable only in the case of monodentate ligands. Got it now?
Yes, sir.
Yes, very good. So try to solve the total number of coordination isomers in this example. CO NH3 taken 6, Cr CN6. CO NH3 taken 6, Cr CN6. This was a complex given to you. What is the total number of coordination? What is the total number of coordination isomers?
6.
6, right?
Six,
So
sir.
identical or different? Different central metal atom.
Different.
No, different central metal atom. Different central metal atom means coordination number of isomers, number of coordination isomers is equal to coordination number, that is equal to 6. So 6 will be your right answer. Got it? And we can exchange the ligands NH3 CN, 2 NH3 2 CN, 3 NH3 3 CN, 4 NH3 4 CN, 5 NH3 5 CN, all the 6 NH3. You will be having only one case where you will have 3 NH3 3 CN exchange. That is not an isomer. Remaining all are isomers. So equal number of same type of ligands whenever they are present, that is not included in the coordination isomers. Write down this point also. Try to write the possibilities. Possibilities is, this is one possibility. CO NH3 taken 6, Cr CN6. Yes or no? Next possibility is CO NH3 taken 5. This is a formula. We know these many isomers are there. But what are they? Just try to analyze. You can just exchange one ligand. Exchange 2 ligands. Three ligands if you exchange, you are having ammonia 3, CNC, cyanide also 3, that is not included. Four ligands you exchange. Five ligands you exchange. I'm writing down here. Six ligands you exchange. Okay, this is 1, 2, 3, 4, 5, 6. Only possibility which we have taken out of coordination isomers is whenever the number of ammonia and number of cyanides, so equal number of ligands whenever they are present, that is not taken into account. So remaining all are coordination isomers. If you list them out, 1, 2, 3, 4, 5, 6. So you are getting 6 coordination isomers. This is the way you have to do it. But if you do all this, it takes a lot of time. So that is why the formula has been given. Whenever you have different central metal atom, then the number of coordination isomers is equals to directly coordination number. Coordination number here is 6. So directly 6 is your answer. When you have same central metal atom, number of coordination isomers is equal to coordination number by 2. That would be directly, if you have only cobalt on both sides, that would be 6 by 2, that would be 3. Okay, whenever you have equal number of same type of ligands on both complex cation and complex anion, then they were not taken into account as a isomer. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, very good. Yeah, this is the same formula, whatever I have told you. Number of coordination isomers is equal to coordination number by coordination number for different centimeter atom, coordination number by 2 for identical centimeter atom, and this is applicable for only monodentate ligands. You try to do this example. PT NH4 ZnCl4. What is the number of coordination isomers?
4.
4.
4.
Yes or no? Different settlement atom, coordination number should be 4. For this second species,
1.
1.
1 or
1.
2.
Coordination number is 2.
Yeah, coordination number is 2. So 2 by 2, that would be equal to 1, right? So this is a trick, and this is how you can solve the number of isomers. And these are the different parts of your structural isomers. Okay. Like there is some difference in the structure. We can also look at some compounds. Like there are the next type of isomerism, like ionization isomerism seen, hydrate seen, coordination isomerism, linkage isomerism. After all this structural isomerism, we do need to study about stereoisomerism. Stereoisomerism we have compared with the organic chemistry, cis-trans isomerism, and optical activity. Optical activity is same. Like there we should not have any plane of symmetry. If you have plane of symmetry or center of symmetry or axis of symmetry, it is going to be optically inactive. Here also same scenario. We should not have a plane of symmetry or center of symmetry. The first one is definition is same chemical formula, but orientation and position of ligands in three-dimensional space are different. Same chemical formula is same, but orientation and position of ligands, how they are arranged in space, the difference in the spatial position is going to be present, and such compounds are said to be stereoisomers. Like I have told you, like if you just look at cis-2-butene, like these two methyls are opposite. Trans-2-butene, these two methyls are opposite. Cis-butene, write down. Methyls are the same side. So difference what you are seeing, students, cis means same side, trans means opposite side. So only difference is the spatial position, that's it. So here also stereoisomers, same chemical formula, but orientation and position of ligands in 3D are different. So first difference you can see in the geometrical isomers. So types of stereoisomerism, geometrical isomerism, same chemical formula, but relative position of ligands around central metal atom is different. The position of ligands around central metal atom is different. Here also optical isomerism means same chemical formula and structural formula. Only thing is difference in optical activity. Optical activity means the ability to rotate the plane polarized light. So important condition for optical isomerism, what are the important condition? You should have non-superimposable mirror images. What are non-superimposable mirror images called as?
Enantiomers.
Very good, enantiomers. What are non-superimposable non-mirror images?
Isomers.
Diastereomers.
Diastereomers.
Okay. So here optical isomer should be present. Plane of symmetry should be absent. Plane of symmetry, if a plane of symmetry, POS stands for plane of symmetry. If a plane of symmetry is present, then one part of the molecule compensates the rotation of other part. Rotation of other part. Yes or no? If plane of symmetry is present, one part of the molecule, how much it is rotating the plane of symmetry, the other part rotation is going to be equal but in opposite direction. So these are the basic formulae and basic definitions, but we have to apply it for different types of complexes, for square planar, for tetrahedral, for coordination number 4, coordination number 6. Sorry. So we'll be applying that, students. Just to confirm if this is noted or not. Is it noted everything?
Yes, sir.
Yes. So geometrical isomerism or Sisstran's isomerism. Write down this first point. Linear, triangular planar, and tetrahedron do not show geometrical isomerism. Write down these points. Linear, trigonal planar, tetrahedron, they will not be showing geometrical isomerism. So whenever we have a coordination number 2, what type of structures we are getting? Linear structures. So coordination number 2 means 2 ligands are there or 2 coordinate bonds are formed. So metal is forming 2 coordinate bonds. So ligand, let us say 2 ligands, the same or different, whatever it might be. So ligand 1, ligand 2. From the ligands, electrons are donated to the metal. You are having one coordination bond, same bond. But these 2 bonds will try to separate themselves by a maximum distance. Why? To have minimum repulsion. So how much is separation? 180 degree. Yes or no? So metal will form 2 bonds, ML1, ML2, and the separation is going to be maximum, so 180 degree. So SP is the hybridization, linear is the shape. No geometrical isomers, no optical isomers. Because there is no question of geometrical isomers, because they have to be completely opposite. That is the only possibility. You don't have other possibilities. Yes or no? There is no other possibility of ligands, positioning of ligands. They are completely opposite. So no geometrical isomers, no optical isomers. Coordination number 2, linear. So no optical, no geometrical. That is your animation view. Coordination number 3. Coordination number 3 means what is the shape? Coordination number 3.
Triangle.
Diagonal plane.
Very good. Trigonal planar. So trigonal planar means you should have 120 degree bond angle. Yes or no? And if you consider any 3 points in space, 1 point here I have considered, 1 point here I have considered, 1 point somewhere here I have considered. With the connecting all these 3 points, I will be generating one plane or not? Yes or no? If I try to connect 3
Yes.
points, yes. If I try to connect 3 points with straight lines, like 2 points, if I connect with one straight line, other 2 points, another straight line, other 2 points, other straight line, I am generating a triangle. And there should be a plane passing through that triangle. So that is why the name triangular planar or trigonal planar. In this case also, the ligands are forced to be at a position of 120 degree. Why? Why they are forced? To maintain minimum repulsions. Yes or no? So the shape here is trigonal planar, sp2 hybridization. Is there a possibility of changing these positions? No, they have to be present at 120 degree only. But some people may ask a question, sir, why can't you have ligand 2 here, ligand 1 here, ligand 3 here? Can I have this as different isomer?
Sir, there is symmetry.
They are same, right? Yes or no? Ligand 2, ligand 3, and ligand 1, their positions are same. So if I change the position of this ligand, keep it here, and if I change the position of this ligand, keep it here, and if I change the position of this ligand and rotate it here, that doesn't mean I have actually done a change. So I have done a change means there should be some change in the bond angle. Yes or no? So there should be some difference in the angle between 2 ligands that should be encountered, not just positions. So it is sp2 trigonal planar, no geometrical isomers. And why no optical activity? Coordination number 2, no geometrical, no optical. No geometrical because only opposite position, that is the possibility. No optical, why in coordination number 2? In coordination number 2, why there is no optical activity?
Symmetry.
If ML1L2, if ML1L2 is the linear molecule, can I have a plane through which it is symmetrical? Like I'll be taking a paper now. Okay, like this is my molecule. This pen, you can see this pen, right? This pen, at the center I have metal. This is ligand 1, ligand 2. Now this is my plane. Okay, this paper. I am passing this plane to this particular paper. With respect to this plane, is this molecule symmetrical or not? So the plane in which the molecule is present, that molecule is symmetrical with respect to that plane only. So whatever the plane in which the molecule is present, the molecule is symmetrical with that plane only. So plane of symmetry is present. So when there is a plane of symmetry, there is no point of optical activity. Got it now?
Yes, sir.
Yes, sir.
Yes. Similarly, triangle means I have told you, here I have a point, here I have a point, here I have a point. Wherever the points are there, I'll keep a plane. Whenever the plane is there, on that plane itself we have symmetry. So plane of symmetry present, plane of symmetry present, no optically activity, no optical activity. Next, coordination number 4. Coordination number 4 means what are the two possibilities you have? Coordination number 4 complexes, what are the two possibilities? You can have hybridization sp3 or dsp2. sp3 means what? Tetrahedral shape. dsp2 means
Square
Square
planar.
plane.
square planar. So you have two possibilities here. Coordination number 2, coordination number 3. Coordination number 2 means linear. Coordination number 3 means trigonal planar. Coordination number 2, sp hybridization. Coordination number 3, sp2 hybridization. Coordination number 4, you can have sp3 or dsp2. sp3 or dsp2. Whenever it is sp3, it should be tetrahedral. Tetrahedral means you know. So like if you have my wrist as a metal atom, one ligand is above like this. So 3 ligands will be downward like this. So if one is above like this, the other should be in this way, other in this way, other in this way. So this is what you will be having tetrahedral, and the bond angle is 109 degree 28 minutes. Now in the tetrahedral and in the square planar, we have to study geometrical and as well as optical. So this is your tetrahedral, students. Metal, ligand 1, ligand 2, ligand 3, ligand 4, and again same metal, ligand 1, ligand 2, ligand 3, ligand 4. Square planar means there is a plane in which all these molecules present. Can I ask a question? Like in square planar complexes, do we have optical activity or not? In square planar complex, do we have optical activity?
No, sir.
Why?
Plane
There's
of
a plane,
symmetry.
right? Yes or no? There's a plane, right? So like I have a molecule like this, and if you look at this plane, in the plane in which the molecule is present, that is said to be a plane of symmetry. Since that is the plane of symmetry, so there is no possibility of optical activity. But yet there is an example. There is an exception case where a square planar complex is optically inactive. That we will be giving later. But most all square planar complexes, you can say a statement, all square planar complexes are optically inactive. Optically inactive. Tetrahedral complex, optically active or optically inactive? Square planar done. Okay, dsp2 hybridization. So you will be giving complex. From the complex, you need to know whether strong field ligand is there or weak field ligand is there. If a strong field ligand is there and pairing happens, then the inner orbital complex is formed. If the inner orbital complex, dsp2 will be the possible hybridization. If dsp2 is hybridization, then you can say, if dsp2 is hybridization, then you can say, yes, the shape is square planar. If it is square planar, no optical activity. If it is tetrahedral, is there an optical activity or not?
No, sir.
No? Write down this point. No tetrahedral complexes will not have any geometrical isomers, but may show optical activity when all the 4 ligands are different. When all the 4 ligands connected to the metal are different and it is forming a tetrahedral complex, in that case, what we can say is that metal behaves as a chiral carbon and it will have chirality. Whenever it has chirality, it should be optically active, right? This is a condition. But all tetrahedral complexes will not have geometrical isomers. Why? Because one ligand or the other ligand, they are present at the same distance, what bond angle would be same. Like if I change the position of L1 and place it at L3, and L3 if I change and place it at L4, L4 if I change and place it at L2, nothing is going to happen, same complex again. Because L1 is at an equal angle of 109 degrees with L2, L3, L4. 109 degrees is the bond angle. So no geometrical isomerism for all tetrahedral complexes. Tetrahedral complexes. Earlier what we have said, for square planar complexes, no optical isomerism, but it will show geometrical isomerism. For tetrahedral complexes, no geometrical isomerism for all tetrahedral, but it can show optical isomerism when all the four ligands are different. When all the four ligands are different. Is that clear, students?
Yes, sir.
Yes, sir.
Yes. Yeah. Square planar is DSP2. No geometrical isomerism, but may show no optical isomerism, but may show geometrical isomerism. Simple logic. Square planar, in the name itself, plane is there. Whenever plane is there, there should be a plane passing through that particular molecule. So plane of symmetry is there. Plane of symmetry is there means no optical activity. No optical activity, geometrical isomerism can be possible. Why? Why geometrical isomerism can be possible? Why in the tetrahedral I am saying it's not possible, but in square planar we are saying it is possible. Why?
Because some ligands can be placed opposite to each other, generating
Yes.
cis
If I
and trans.
change the very good. If I change the position of ligand in the tetrahedral, I am getting the same compound. If I change the position of ligands also, then I am resulting in the same molecule which has same bond angles. But if I do the same in square planar complexes, if I change the position of ligand L1 to here and L4 to, if I switch these two ligands, then with respect to ligand 2, earlier it was at 90-degree angle, but with respect to ligand 2, now L1 will be at 180-degree angle. Yes or no? So position changing is getting a different molecule. So that is why square planar can show geometrical, but tetrahedral cannot show geometrical. Right? Very good. Yeah, these are the conditions. So what are cis, what are trans? Earlier cis means same sides. Trans means opposite sides in your organic compounds. Now what is cis? In square planar complexes, at 180 degrees same group is present means trans. 180 degree means opposite side only, no? Exactly opposite. 180 degrees same group present means trans. 90 degrees same group present means what? Cis. At 180 degree if we have the same group, then it is said to be trans. At 90 degree if we have same group, then it is said to be cis. And we have the terminology now. Capital M stands for central metal atom. Small a, small b, small c, small d, e, f. With the small letters, what are they? They are said to be monodentate ligands. Capital A, symmetrical bidentate ligand. Capital A, capital B, unsymmetrical bidentate ligand. You may ask a question, sir, why are you writing all this? Why can't you write the complex directly? Because we have to look at the probabilities. How many types of complexes we can write, and with every complex, how we can categorize the number of optical isomers, number of geometrical isomers. So that is easier when you go proceed in this manner. So this is the terminology we are going to looking at in the upcoming slides. Capital M, central metal atom. A, B, C, D, E, F, monodentate ligands. A, symmetrical bidentate ligand. A, B, unsymmetrical bidentate ligand. Got it, students?
Yes, sir.
Yes. So I'll give one complex to you. You try to figure out. Yeah, this complex Ma4. First complex Ma4. How many geometrical isomers? How many optical isomers?
No geometrical isomerism and no optical isomerism.
Yeah. First, we are looking at square planar complexes. Ma4 square planar complexes. Square planar complexes. Because Ma4 does not mean we know from Ma4 it is having coordination number 4. Coordination number 4 can be square planar or tetrahedral. So we are looking at square planar complexes. Coordination number 4 square planar means you are having M and you are having all 4 ligands which are same. First thing, square planar, there is a plane passing through that particular molecule. So plane of symmetry present. So no optical activity, no doubt in that. Geometrical activity is also not present. Why? If you change the position of any of the ligand, are you getting a different compound or same compound? Same compound, right? All the ligands are
Same.
same. Yes or no? Same compound. All the ligands are same. So no geometrical, no optical. Very good. Ma3b.
No geometrical isomerism.
No
and
geometrical,
optical
but I have.
Yes. Ma3b in the square planar complex again. Ma3b in the square planar complex. Again, square planar means no optical activity. Ma3b. So 3 ligands are same. Only one ligand is different, B. So you change the position of this B to any particular way. So you keep the position of B here, or you take the B to the other place, you take the B to this place. Whatever the way you place, or whatever the way you change the position of B, you are getting again the same compound. So no geometrical isomerism again. Yes or no? No geometrical and optical. Ma2b2.
2 geometrical isomerism.
Okay. Next to go with the coordination number 4. Write down these molecules, all of you. Ma4, no geometrical, no optical. Ma3b, no geometrical, no optical. Ma2b2, no optical isomers, of course, because it's square planar complex again we are dealing with. But 2 geometrical. What are those? Where the 2 A groups are at a 90-degree angle, same groups present at 90 degrees, that is cis. Yes or no? Same group present at 180 degree, that is trans. So Ma2b2 will not have any will not have any optical isomerism, but it will have 2 geometrical isomerism. Which one is cis? Cis means the same groups at a 90-degree angle. Trans means the same groups at 180-degree angle. Is that clear, students?
Yes, sir.
Yes. Very simple, right? Yes. These are the animations where you can see the 2 groups are exactly 180 degree, that is trans, 2 groups 90 degree, that is cis. Write on this. Geometrical isomer cis and trans of a PT-NH3 taken twice, Cl2. Cisplatin, transplatin usage. Cisplatin is used as an anti-cancer drug. Okay. PT, platinum is the metal, central metal atom. 2 NH3 groups and 2 Cl2. So ammonia is the ligand. 2 ammonia are there, 2 chlorines are there. And if you look at the arrangement, it is similar to Ma2b2 system. Ma2b2, because metal, central metal atom is platinum. One type of ligand A is ammonia, other type of ligand B is chlorine. Ma2b2 system. Ma2b2 system can exist in cis form and trans form. Whenever it is in the cis form, it has anti-cancer drug. It is used as an anti-cancer drug. That means whenever you change the spatial position of one group, the chemical reactivity changes. That point you need to understand. The chemical reactivity of a drug depends upon the spatial positions of groups. Right on the point. That means the chemical reactivity of complexes changes when the spatial positions change. When the spatial positions change. We have to remember these points as well. Okay, we have to remember all these statements, like when it is going to be acting as a, like cisplatin is used as an anti-cancer drug. So we have to remember that questions can also be asked. Whereas transplatin is not acting as an anti-cancer drug. Note down, all of you, note down and let me know if you're done.
Yes, sir, done.
Done. Very good. MA to BC. MA to BC. No optical activity because again I'm talking about square planar complexes. Geometrical isomers would be there or not? Now you have two different groups. B and C are different, but two same groups are there. Whenever the two same groups they are at 90 degree, that is cis. Whenever the two same groups they are at 180 degree, that is trans. Again our condition holds. Like if I change the position of, this A and this C, like two same groups I'm getting at an angle of 180 degree. Then if I switch this, then I'm getting trans. And if they are at an angle of 90 degree, that is said to be cis. How many geometrical isomers? Two geometrical isomers. What are those? Cis and trans. MA to BC. Yeah, we'll discuss about ruthenium complexes, Keshav. Okay.
Okay, sir. MABCD, write down. MABCD complex, how many geometrical isomers are there? How many optical isomers are there? First, let us take a square planar. You take square planar first. Although here tetrahedral figure is given, you take square planar. MABCD, you don't know what is metal, what are ligands, you don't know, right? Two possibilities are there. Coordination number is 4. Square planar is a possibility, tetrahedral is a possibility. You take square planar and figure out how many optical activity or how many optical isomers, how many geometrical isomers. All the 4 ligands are different. Anyone?
Sir, in tetrahedral optical activity.
Yeah, in tetrahedral, optical activity will be there. Like MABCD, if you first go with the tetrahedral, I have told you to go with the square planar. Okay, anyways. So MABCD, all the 4 ligands are different. All the 4 ligands are different, but if you change the position of any of the ligand, do we have the change in the structure? No, because all are at an angle of 110 degree. So tetrahedral complexes will not show geometrical isomerism, no geometrical isomerism. But all the 4 ligands are different. So how many optical isomers? All the 4 ligands are different means we can have 2 mirror images, non-superimposed mirror images. So the 2 optical isomers are possible. Is that clear? MABCD
Yes.
complex. Yeah, MABCD complex, if you look at tetrahedral fashion, it can show optical activity because all the ligands are different. How many optical isomers are there? 2 optical isomers. But it will not show geometrical isomers. Why? Because the spatial positions of ligands, they are all going to be fixed. If you change the positions also, you are not getting a different structure. DSP2,
Sir,
MABCD same.
so why was
Yes.
it a
Note
two optical isomerism?
2 optical isomers are enantiomers, no, non-superimposed mirror images. Like one optical isomer will be in such a way such that it will rotate the plane polarized light by a clockwise direction. Other will be in the other way. Okay,
Yes.
non-super, like if I keep a mirror here, you will get one more image, right? Those 2 are mirror images. Okay.
Yes, sir.
Yes. Whenever we have an chiral, this metal atom here behaves like a chiral carbon. Not exactly like chiral carbon, similar to that chiral carbon. So whenever you have all 4 different groups, you can place a mirror, you get a mirror image. This compound and its mirror image both are optically active. So that is why 2 optical isomers. But changing the position of any ligand is not giving you a different compound. So no geometrical isomers. Got it, Nandana?
Yes, sir.
Yes. Now this MABCD, sp3 is the first possibility we have looked at. Then MABCD, DSP2. DSP2 means now we are talking about square planar. Now look at optical isomers, how many are there?
0.
0, because square planar means optically inactive. And geometrical isomers?
1.
So we have to write AM, A, B, C, D. Let us give me priority to A and B. Okay, with respect to, since A and B are at 90 degree, I am saying this as cis. Let us say A and B are given the same priority now. Now A and B, I will change I will keep them same, but I'll make the change in the C and D positions. It is also cis or not? The first component, second component, are they same or different? Look at this compound, students. First compound, what I have considered, metal M is connected to A, B, C, D. All 4 ligands are different. All are monodentate ligands. And now I am considering A and B are at an angle of 90 degree. So I am treating this as cis. Treating A and B as first priority groups. Like we have cis trans is there, similar to that. ZD isomerism is also there, if you remember, in organic compounds. Remember or not, anyone? Z, cis, E, trans. Similar to that, here the groups may be different. If you don't remember also fine, don't worry. Here the groups may be different, but let me give some priority order, or you can just consider any group, any 2 groups arbitrarily. I have considered A and B. Since they are at a 90 degree, I am calling this as cis. Keeping them at 90 degree only, so again cis, I have changed the positions of C and D. Now I can say this is the first compound, this is the second compound. They are different or not? Yes, they are different. Why? Because in the first compound, A and D are also at 90 degree, but in second compound, A and D are 180 degree. So first and second compound are different. Now I have made the change, because already C and D positions are changed. Now I have made a change in the A and B positions. A and B are now at an angle of 180 degree. So this should be trans. And now I have C and D, right? C here and D here. Now if you change the positions of C and D again, this is a third compound. Again the trans I want to write like this. Is that a different compound or same compound? A and B 180 degrees. I am keeping D here, I am keeping C here. Is it a fourth compound or same as third compound?
Same as third.
Same as third, right? So you cannot include this. Is there any other possibility you check out? If you change already cis, in the cis configuration, you have seen 2 possibilities already done. In the trans configuration, if you want to fix A and B at an angle of 180 degree, only 1 possibility is there. So these are the 3 possibilities which you can have. You can't have any other isomer. So DsP2 MABCD complexes will not have any optical isomers. That is known because of plane of symmetry. But they show geometrical isomers. How many geometrical isomers?
3.
3.
Write down. 3 geometrical isomers are shown. What are those? 2 cis and 1 trans. You may argue like, sir, why you are calling that as cis, since they are not same groups? You consider any 2 groups, random groups. You consider A and D also, not an issue. If you consider A and D as your groups, then it becomes cis. It becomes trans. It becomes again cis. Yes or no? A and D. So any 2 groups you consider. Any 2 groups you consider and try to change the positions of ligands, then you will be getting 2 cis and 1 trans. So 3 geometrical isomers are there. Yes or no? 3 geometrical isomers and no optical isomers. That is the scenario in M, A, B, C, D type complexes. Is that clear, students?
Yes, sir.
Yes,
Yes.
sir.
Okay, fine. These are the different examples as of now. We have just considered monodentate ligands. Tomorrow we will be including bidentate ligands and look at optical activity, geometrical isomers. In again, coordination number 4, coordination number 6 complexes. Fine, students. Thank you all, everyone. Bye-bye.
Thank you, sir.
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 Thank you, sir.